are the dimensions where we have to think about, or what we have to use about for roughly estimations for shielding of, for example, iridium 192 source, roughly about 70 centimeter, low dose radio brachytherapy around 50 centimeter, superficial radiation 50 centimeter. These dimensions don't tell you out of which material, and this is what the comment here for the superficial radiation is. This could be done more efficiently using lead, of course, but these are the numbers of the dimensions is not related right now to any material. So a linear primary beam, roughly about 2 meters, and the cobalt therapy scatter and leakage shielding about 1 meter. This is, as I mentioned, these are very rough estimations. Next one. If we are looking of the what are the effects where we have to deal for the radiation protection. So we have, as you may know, we have photon interactions. We have the interactions, they are related between, they are energy related and a kind of density related to the atomic number. And you see the green area is at the bottom. It's the patient in general in terms of his atomic numbers up to set of 20 for calcium, let's say main part of the bone. But normally humans are mostly made out of water. That means the set of humans is very, very good estimated by oxygen and hydrogen. That means the set is between 8 and 1. And you see for the radiation, for diagnostic radiology, we are in the bottom line. For the patients, we are between the photo effect and the Compton effect. So we have this is for imaging. This is our basic line for the imaging. If you want to go to shielding, we go up in the set direction. We are going up to the set of 82. That's lead, and you see we are for the diagnostic radiology. We are complete with our high density and high set. We are completely in the photo effect area. The same thing in nuclear medicine. The energies around 500 kV. We are also for the high set. We are also in the area of the photo effect, of the dominant photo effect area. That means we could force for the high density area. We could force in these areas the photo effect. That means we have with high set material a good shielding effect. Coming to the conventional radiation therapy, you see the blue part of the diagram. Also in the background, at the bottom line, we have again the patient area, and you see if we go upstairs, up in the shielding area where we need high set to protect the radiation, and then you see we have also photo Compton effect, and the higher the energy is and the higher the set is, we have a paired production dominant part. So we have for this pair production dominant area, we have a kind of activation, and this is what I will point out later on. Another for a definition is good to know. We will talk about half value layer and tenth value layer. That means a half value layer is the thickness and the thickness of any given material, where 50% of the incident energy has been attenuated by this by an half. So the half value layer of a material is energy depending and depending on the density. So you can find a lot of lists where you have listed for a specified energy a half value layer for specified material, or in the other hand, also a very common value is the tens value layer. So if you go to the next slide, yeah, you see this is how it works. You have energy like, let's see, cobalt 60, and you have a half value layer here in millimeters or inches for concrete, steel, lead, and tungsten. These materials, let's say 60 millimeters of concrete, minimize the intensity of cobalt 60 by a half for a given situation. And you see, if you have a higher density, you need less material or less thicknesses to have the same effect for the same situation. So you could say, if you want to shield a given situation, for example, cobalt 60, you can do this with uranium, and you need this is the thinnest layer you can have to shield this intensity by a half. But you could imagine in radiation therapy, half of the intensity is not enough. That means you need more than one half value layer to be in a situation that you have a proper shielding, for example, to a public area. And you see down in the bottom, you see the peak voltage also for superficial combinations. You see 50 kV, 100 kV, 150 kV. That's a typical diagnostic area, for example, as well. Not only superficial machines for radiation therapy. And you see the number of lead you need for a half value layer is much lower, depending on the energy. And you also see you have a corresponding concrete half value layer, and then you see these are normally you could achieve a good radiation protection in the radiation radiodiagnostics by very thin layers of lead and with normal walls and with normal wall thicknesses. Yeah. Yeah. Next slide, please. Next. Yeah, here's an example for the tens value layer, because if you have very high energies like 5, 6, 10, 15 mega electronic volt, you see you will have a tens value layer give you better information that you are able to achieve at the end the complete protection by a given for a given energy. I would start with the radiation protection issues in radiodiagnostics. I estimate you have energy in the radiodiagnostics, kV energy of the X-rays. Let's start by 40. Sorry, you have in radiodiagnostics you have a typical value for diagnostic examinations is, for example, mammography has a typical kV, typical energy of the X-rays of 26, 27 kV. A chest X-ray is done with 120 kV. So this is the numbers of energy where you have to deal in radiation, in radiodiagnostics, and this is related then to the needed tens and half value layers in your for your radiation protection. And you see this here, a typical and a very common shielding material in radiodiagnostics is lead. You have this in lead-prones and so on. And you have in this area you could force for this energy, and in this with this energy and with the lead-prones you could force for direct radiation and for scattered radiation. You could force completely the photo effect for a lead-prone, and you have a very good shielding effect by forcing this photo effect as a shielding effect. You see this here. You have the scattered radiation out of the patient from the image intensifier, and you see down on the table you see the X-ray tube, and you see without the protection you have a scattered area in the down the patient, and in the same height of the patient you have the scattered area, and you could minimize this by a conventional lead shielding. And this lead shielding is around in the equivalent of 0.3, 0.2, 0.5 millimeters. Yeah, the next one. Yeah, this is a typical examination situation for in the radiodiagnostics. You see. On the left-hand side is a medical doctor who does the examination. On the table is a patient. The medical doctor, the shielding option that he has is a scatter from the patient, so he has no direct radiation, and the shielding effect is done by the lead-prone. You have only you can shield it the complete scattered radiation down to 99%. The patient is on the table, and next one, please. And you see that's a bit only to have a correlation. The patient has to be shielded by the patient body has to be covered by. Oh, back, please.
Oh, sorry. No.
Back.
Okay.
Back.
This is where we were.
No, back. So now here. Now we are right. So.
Yeah.
Once next, please. So now we are in the right position. So you see, no, once back.
This is back.
Yeah, now we are now keep this, yeah. So you see, if you want to shield the patients, you see at the left-hand side an example for shielding the gonads. That means if you put a shielding protector, and in this case it's a equivalent of 1 millimeter lead, you could shield this part of the body in the primary beam by 100%. That means a typical kV, typical energy in radiodiagnostic to do these images is 80 kV or 90 kV. So in this area with 1 millimeter lead, you are able to shield, to force in this 1 millimeter lead this photo effect, and you are able to shield this area complete also in the primary beam. And the other end, but you need a higher number of material to get this part shielded, and not you are in this, you are here in a primary situation, that you have a primary beam to the patient, but you see the medical doctor, he is in the scattered area. So these are a different situation, but he's working with the same kind of energy, but you have lower scatter and higher primary beam. Yeah, next one. So, and this is what you have in radio diagnostics. You could shield all the persons who are around the patient in an examination situation. All the patients who are in this situation, they are shielded by these letterprones, and these letterprones are very effective in shielding against the scattered radiation out of the patient. And and the scattered radiation is the only source for radiation, and is the only reason to wear this letterprones is a scattered radiation out of the patient. Otherwise, if there is no patient during the examination, there will be nearly zero scatter, and you will have no exposure around. So there are different designs for these letterprones. I would go deeper in this case. So would you go to the next slide, please? Yeah, the same thing. If you want to do the shielding of the patient, this is for especially for the CT examinations. You have very low and very thin lead and composite lead parts where you can shield, example for the eye lens or the thyroid, and you can shield these parts of the body very effective by very thin layers of lead, and in the combinations energy and material. Next one, please. Yeah, we are coming later on the situation in radiation therapy as well, but also in radio diagnostics. The machines who working in these, for example, this SIGO, this angiography unit, has a very high degree of freedom, and you are able to bring this machine in a very complex positions. So you have a real complex scattered radiation around the patient, and this makes things in these hybrid OR rooms very complicated to be that people who are around in this OR theater, that they are shielded in a right manner. Yeah, next one. This is a typical. This is a layout of a CT scanner. You see this CT scanner is here in the middle. And you see there are in this green area there are windows, and this is prior to the installation of the scanner. You have a calculation that you can say you want to have in very specified areas. You will be below the limit values, and the radiation protection has to achieve these values. And you can calculate by the given energy, because you see it above it, where the maximum energy of this computer scanner is 120 kV, and you see there is a workload of 20,000 milliamps per minute and week, and based on these numbers you can calculate what is the needed shielding that you achieve these limit values, because you are in a public outside the building and these and so on. And this is what it called the radiation protection plan, and this is also part of the construction plan. The construction plan always goes beside the radiation protection plan. And you see the operating area for the CT scanner on the right hand side, and you see there is a window as well. This green lined area is a window. So someone who is sitting and operates a machine has to be shielded in that manner the place where he sits is a public place, and the limit value for the public place is 1 millisievert per year. So that means this person who sits in front of this windows and operates a machine has no further exposure than if he were in this time in the public. Yeah, next one. Yeah, I'm still talking about the relation between the shielding material and the given energy. I have talked about the radio diagnostics, where the energy between 25 kV and 120, 150 kV in maximum is a given energy. So for this given energy, you have a given material where you can shield this energy in a proper way to achieve the given limit values. And you see in nuclear medicine, things are a bit different. So a very often used material in nuclear medicine is technetium-99m. You see this has an energy of 140 keV. And what's also very common for PET CTs is fluorium-18, and you see there is an energy of 511 keV. So shielding for the iodine-131 is also very common, and you see the half-life values are for fluor-18 is relatively short. For technetium-90m is 6 hours, and the other is 8 days. So with this fluorine and 18, you have the problem that is the half-life is relatively short, so you have to have this this isotope. If you have it, you have a very short time to have for your examination. And you see the given half value layers and the given tenth value layers for this material. If you want to change by a value of tenths, you need 16 millimeter lead. And we need only parts of a millimeter for shield the energy of diagnostic area in the diagnostic area. So the shielding material is the same, or mostly the same in nuclear medicine, but the thicknesses of the shielding material will increasing. Yeah, the next one. Yeah, again, to have this in the back, and you see here the typical situation for preparing these isotopes before the injection to the patient, and you see here this lead bricks, and these lead bricks are having, let's say, an estimated thickness of 3, 4, 5 centimeters. So the situation is you have a high energy, and you have to handle this energy inside an area. So you have shielding inside for preparation of the isotopes, and you have to shield, of course, these rooms to the outside. And in this case, you have to have the dimensions of the shieldings are also higher. Next one. Yeah. Also, what's very special in nuclear medicine is you have to prepare the isotope in a syringe, and because you have to inject this isotope into the patients, and you have, as we have seen, you have more than 500 keV for fluor 18 isotope for PET-CT examination, and you have to prepare, you have to transport, and you have to inject these isotope into the patient. So you need, for each step of this examination, you have to shield the devices needed with you have to shield these needed devices before you have the inject the whole isotope into the patient. And you see here are very special transport mechanisms, and you see in the lower left corner, you see what is the difference in terms of the higher energy of fluor 18, of the radiation protection, of the syringe protection, and you see you have for technetium 99 you have only a need for 2 millimeters lead, and for the fluor 18 you have 8 millimeters. So you have a higher energy, you have a higher half value layer, a higher tenth value layer, and in this case, at the end, the thickness of the material increases. Yeah, next one. Yeah, I'm coming now to the main objective, that's shielding in radiation therapy, and I think the actual report where all these things are ruled is NCRP report 151, and I have also some examples, and I have also some images taken out of this report. Yeah, next. Yeah, here is the energies we have to deal in radiation therapy are much higher than in nuclear medicine. Nuclear medicine, you have seen fluor 18 for patient examination between 500 and 600 keV, and you see the lowest energy you deal normally in radiation therapy is cobalt 60. It's roughly 1.13 MeV, and you have linear accelerators with 6, 15, or 18 MeV, and you have the ions like protons, for example, with 300 MeV. So you have a much higher energy, and if you remember the next one, yeah, and if you remember about this image, and you have a look at the right hand part of this diagram, you see that if you are going above 10 MV, sorry, yeah, if you are going above 10 MV, you reach the pair dominant the pair dominant part of this drawing, and at this part you could say activation and neutron production starts. So we have with the higher energy, we have problems in radiation protection, not only to protect against the photons, we have also new issues regarding activation by neutrons. Next. Yeah, this is a ground map of our department. You see, we have different linear accelerators. In the left, at the left-hand side, this is the ordinary shielding, with these are high-energy machines. At the upper left, there is a low-energy machines. At the right-hand side, and the upper right-hand side, We have a gamma knife with an energy of around 1.2 MeV. This show you a bit the dimensions you need to shield this area. So we are now above of centimeters, millimeters, parts of millimeters. So we got, if you are remembering the one of the first slides, we are now in the area of meters. Yeah. Yeah. Next one. Yeah. Yeah, the shielding basics for radiation therapy. Relevant shielding in the treatment room needs, we are talking about primary and secondary barriers. We have the surrounding areas, what's around your treatment rooms. There are offices, public places, or other controlled areas. We have different room designs, for example, with or without a maze. And we have, let's call it side effects in relation with a maximum photon energy, more than 10 MeV. You remember that we have activation processes above 10 MeV. So above 10 MeV, we have air activation processes. We have a need for additional neutron shielding. Neutrons are completely different to photons in shielding. Photons, you shield photons by high density and a high thickness. Neutrons are completely different, are upside down. The shieldings of neutrons happens with low density. So a typical shielding material for neutrons is, for example, wax. And we have activation of items in the beam above 10 MeV. Next one. Yeah, here is this what I've talked about. You have an activation of air, and this has consequences for the staff. For example, the employment of pregnant women in these areas. If you have a linear accelerator with, let's say, 15 MeV, you have activation of air in the treatment room short after the treatment. You see the half value time of this nitrogen 14 is around 10 minutes, and the oxygen is only 100, roughly 2 minutes. Yeah, and the energy is very high. These are 500 keV. So in our radiation protection regime, pregnant women are not allowed to work at accelerators with a higher energy than 10 MeV because of these activation processes in the air, because pregnant women are not allowed to expose by isotopes. And the other hand is you need a higher power of the air condition, because you have to eliminate this activated air in a specified time. And on another hand, you couldn't operate this machine if the air condition is not working. For the protons, you have, for example, if you have the normal shielding with concrete and to stabilize it by iron inside, you have iron activation of the iron in the concrete to ferrum 55, and you have a 230 keV line and a half value time of 2.37 years. So this has to do with what's happening after the operation of a proton unit, what's happening with parts of the treatment room if you have such a relatively high energy left for two or 3 years. Yeah. Next one. Yeah, we have it to give you an idea about the tense value layer. You see, we have here different diagrams. What the NB means, the NB line, NB 2.3 means we have a regular density of concrete. These are 2.3 grams per cubic centimeter, and we have the BB 3.5. That means high density concrete of 3.5 gram per centimeter. And if this is a bit animated, so could you have, I think this is four animation steps in. Could you hit 4 times? Yeah, you see here the 6 MV. 6 MV, we have a tense value layer for the rough calculation. We have a tense value layer of 23 centimeter and of regular density concrete, and we have a regular density concrete of 34 centimeter, and we have a high density concrete tense value layer of 23 centimeter. So if we are going now, and normally you could roughly calculate for 6 MV, you need around 4 to 5 layers of concrete to fulfill the limit values. So we are talking about this is what I have talked at the beginning. Now, if you have 4 or 5 times that of a tense value layer, you see we are above 1 meter. Yeah, of 1 meter wall thickness of regular or high density concrete. So if you are going for 15 MV, hit it also 2 times. Please 2 times for hit it to have the animation for the 15 MV. Yeah. Next. Yeah. You see, for the conventional concrete, we are for the NB 2.3, we have a tense value layer of 48 centimeters. So I have mentioned we need for a proper shielding, we need around 3, 4, 5 tense value layers, and then we are around 2 meters of wall thickness for a 50 MV machine. So the discussion is now: do we need this high number of energy for such a machine? If you compare the depth dose curves for 6 and 15 MV, yeah, you gain not that much in terms of you have a better I would say the dose maximum for the 15 MV depth dose curve is around 2 centimeter, 2.5 centimeter. 6 MV is stable at 1.5 centimeter. So at the end, you have a much higher shielding, and at the end you have to spend a lot of money for the building to have a proper shielding for a 15 MV machine than for a 6 MV machine. So the discussion is, if you need more than one energy, what should be the second energy? We have historically 6 and 18 MV. 18 MV is way too much. With a new technology, with a new techniques like rapid arc or VMAT or IMRT, you could achieve very good conformality and very good homogeneity in the target, also with lower energy. So it's not really necessary to go above 15 MV. And there are a lot of people saying, okay, 6 and 10 MV is very good for the therapy. Yeah, next one. Yeah, you see this. The next one aspect is this example for this is the machine that was replaced later on with a lower energy. This machine before had a lower energy, and now it was replaced by a higher energy machine. And you see there was an additional shielding necessary. You see these black lines. These are iron plates to shield. But you see at the end, this construction is done by a combination of lower density concrete, and you see in the area of the primary beam there is a high density concrete, and this is to shield with the highest density the area of the primary beam, and use the lower density of the concrete for the scattered area. And you see there are roughly also 1 meter, 80 centimeter, nearly 2 meters. So conventional concrete. These are very massive buildings, and you could imagine this is also a very expensive way to build those buildings. Next one. If you compare the same dimensions for a cobalt bunker, you see you could roughly say this is half the thickness. You see here the concrete of the low density has a dimension of 60 centimeter, and the area of the primary beam are 75 centimeter. The problem is a bit another way around. If you have a given cobalt machine in a bunker and you want to exchange this machine by a linear accelerator, then you could imagine that the problem starts with the radiation protection of these machines. You have to increase the radiation protection of a given cobalt bunker. You have to increase the radiation protection for this machine massive. But where should you put these additional shielding on the walls? Inside, then you have a smaller room. Outside, maybe you have this bunker is underground. You have to this is a complete different construction method. So these problems are very high. These machines are at a lot of countries. These machines are very common. So if you want to exchange a cobalt machine by a linear accelerator, you will have a really big radiation protection problem in terms of the constructional protection is too low. Yeah, next one. Yeah, you see how the other parts, you have to a room door. The door has to be open, and these doors are also really massive. You see at the left-hand side a conventional door. You see the worker here is filling the door with lead, and you see this green part. This is a low density material for the neutron shielding. And on the right-hand side, there's also a very special construction. You see the treatment machine in the background, and this is a mazeless treatment room. I come back on this later on. The next one. Yeah, these are typical room layouts, and from the radiation protection point of view, we are talking about primary barriers. These primary barriers are areas where the primary beam hits the walls, and you see the primary barriers are always the thickest part in the room design, and mainly these primary barriers are carried out with high density concrete. And you see you have a secondary barrier. You see the maze is also limited and also guided by a secondary barrier. And you could turn the machine that you have, and then you have to change the secondary and the primary barriers. Yeah, the next. Yeah, this is also animated. Could you hit several times that we get? 3-4 times hit. To start the animation. Yeah. So we have the primary beam, we have the radiation source. Next. Go on. We have the leakage of the machine itself, and we have the leakage out of the patient, and we have the reflected leakage as a secondary radiation from the walls, and we have reflected radiation in the direction as a tertiary radiation in the direction of the door. So the maze has one constructional part. The maze limit the tertiary radiation in the direction of the door. So if you have mazeless treatment rooms, you have to compensate this maze at the end by a thicker door, and this is you have a comfort that you have a shorter way into the room and a more comfortable way into the room, but you have to work with thicker doors. And the shielding in radiation protection is also animated. Could you also hit once or twice? Yeah, you see the radiation, the machine is turning. So did you have you have the radiation, the primary radiation to the left and right, but also to the top. And once back, please. So now it's nearly, yeah, back once. Yeah, so you have different types of radiation. You have leakage radiation, you have primary radiation, and you have the primary radiation around the machine. So if you look at the right-hand side, what's about the top of the bunker? If there are another building, if there are offices, so you have to have you have limit values. You have to achieve limit values at the top. And the other thing is what is left and right of the machine, and these are the conditions you take in account for a radiation protection plan. Yeah, next. Yeah, okay, yeah. So what is needed when we are talking about how to structure a radiation protection plan with the shielding for radiotherapy? Of course, you need an information about the equipment type. In terms of a linear accelerator, you need, for example, the most important part is what is the highest energy. If you have an isotope, of course, you need the source isotopes, the activity, the date of calibration, radiation quality, as that. What is the dose rate, the field size, and are there some additional functionality? This has an impact to the radiation protection, like for example, like the IMRT. So you have to define your workload. You have to define the target dose. You have to define the use factor. This is defined also by the direction of the primary beam. You have to define the distance of the area of interest. You have to define the occupancy of the area to be shielded, and you have to know the limit values in the area to be shielded. Yeah, next one. So, and there are some new issues, and these new issues are covered by the NCRP report 151. There are new types of equipment like the cyberknife. So there is a robotic arm. You see, you have a very high degree of freedom of moving the machine. So at the end, you have no fixed isocenter. The machine is not stable in terms of the isocenter. So for the radiation protection, all barriers are primary. So it's no longer, if you compare this to a linear accelerator, the machine is fixed in relation to the building, and the primary beam is around the rotation of the 360 rotation around the machine. And if you remember also from the diagnostics, if you have more degrees of freedom, the radiation protection situation from the constructional part is more complex. And you have a real complex situation for the cyberknife situation, because all barriers except the ceiling is primary, so you have a higher shielding. Higher shielding for. I think the machine has 4 or 6 MV, so you will have for a building for a cyberknife a higher impact on the shielding than for the same linear accelerator of 6 MV. And also the tomotherapy. Tomotherapy has also an MVCT, and the machine works with the beam stoppers. This is sometimes very useful because the impact on the primary area is lower, and the NCRP report has also regulations now for dual energy machines, room design without maces, varied shielding materials, including composites. These are new materials, and there are more published data on empirical methods. That means there are the question is at the end how to get a proper calculated radiation protection plan. You need at the end you need programs for that, and there are also more empirical methods based on Monte Carlo calculations. Yeah, the next one, yeah. An example how to get a rough idea about the radiation protection for a linear accelerator. You could say, as I've mentioned before, you need the workload. And you can assume the target dose given in the isocenter is 2.5 gray. You have 50 patients treated per day on 250 working days per year. And you have to have and you see here, this is roughly 32 kilogray per year. And you have to take into account that you have additional switch on time for the machines, for example, for the physics QA. If you have total body irradiation, you have also a high number of monitor units to apply by body irradiation. So you have a rough calculation with 40 kilograys per year at the isocenter. That is very conservative, but it's not too high. The next one. Yeah, workload, and this is what I mentioned from the NRCP report. He included now for the shielding calculations new methods, and one of these methods is the IMRT, and the IMRT applies radiation in many field segments, and you always have high monitor units. That means you have high switched on times, high tension mode times for the machines than in the conventional radiation therapy. And the next one. Yeah, this you have this high number of monitor units per field, higher than in the conventional therapy. So the target dose is still the same. So the primary shielding will be not affected by this higher monitor units. However, the leakage radiation can be significantly increases. A factor of 10 is often assumed. This is out of the presentation from the IAEA. Here in Germany, we calculate with an IMRT factor of 4. If you have a conventional machine and you change this machine, or you do an upgrade for the machine for IMRT or VMAT, a typical factor is, let's say, between 4 and 5. That means at the end, if radiation protection was correct for conventional machines, it could mean that the radiation protection couldn't any longer correct for a machine this is used for IMRT. The next one. Yeah, from this I go ahead with explaining the factors who have an impact on this calculation. Fraction of the primary beam in the particular direction, and you see this is from an older version of this report. They have a use factor 1 for 0 degree. That means the gantry is pointing down. 0.5 for 180 degree. That means the gantry is pointing up. And you have 0.25 for the lateral direction, and the main direction for treating this is typical for the 3D conformal area. Mostly the gantry is pointing down. 0.5 is up, so you have opposite fields, and this 0.25 for lateral directions. This is a typical 4-field box, for example. Yeah, next one. Yeah, the use factors for the primary and the secondary shielding. That means the shielding must consider 3 sources of types of radiation. The primary, this is what we had, the scattered and the leakage radiation. So there is no use factor for these 2 kinds of radiation, and so the use factor is 1. So brachytherapy does not apply for any use factors. It's also 1. The next one. Yeah, the leakage, depending on the design, typically is limited to 0.1 or 0.2 of the primary beam. Leakage is also a acceptance part of the linear accelerator. The leakage of those machines has to be below a specified and a defined value. Scatter. This is from the animation you saw on the first. Scatter is assumed to come also from the patient. Yeah, it's difficult to calculate. Normally, what is normally done, you use the largest field and you could measure what's the highest scatter. The lower the energy, the more of the concern for photon beams. So you could measure it, and is also more or less a constant factor for the machine. So next one. Yeah, distance to the point to be shielded, usually measured from the target or the source of radiation. In Linux and isocentrically mounted cobalt units, it's measured via the isocenter. So you have first a typical Linux isocenter target isocenter distance is 1 meter. And very important for shielding, as dose falls off with a distance of squared is the inverse square law. So if you want to have the distance from the isocenter to the machine, you have to and you want to calculate it for one specified point at the wall, of course you have to use this inverse square law rule. The next one. Occupancy factor. This is important for the surroundings. So what is around the treatment room? What is above? What is below? And these areas could be occupied by other persons, or, for example, these areas could be in the public. So you can and you have defined these areas by using these occupancy factors. If you have the occupancy factor of 1, that means this area could be full-time occupied by any individual. So this is typical for offices and some occupied spaces nearby the building, and also for public areas. And so this is, you see this is scales, this factor, and this factor is going down until the factor is going down for areas where the occupancy is getting lower and lower and lower. So the factor is lower as well. So the highest occupancy factor means 100%. This area could be 100% occupied by an individual. That means day and night, 365 days a year. Yeah, next. Yeah, the occupancy factor has a high impact on the. Is this a controlled area? Could you have free access to these areas or not? So, and these occupancy factors is related to the limit values for specified areas. So if you have a room nearby the treatment room, there's a diagnostic room from the radio diagnostics. This is the control room. In a control room, you could have an exposure by 6 millisievert per year. You could use another occupancy factor than for the public. Yeah, next one. Yeah, the basic shielding calculation is based on the NCRP report 151, and the assumptions used are conservative. So over design is common. Normally, it's not to the point. The calculation is not to the point. It's also, and you saw this with a 40 kilogray per year. It's also a conservative assumption. So computer programs, of course, are available in giving shielding in thicknesses of various materials. Yeah, next. You find this example is also out of the EIA program. I would like that you try these calculations by yourself. It's a very simple calculation. Go ahead, please. Next. Yeah, next. Yeah, this example you could try to calculate and can do it by yourself, and you can vary the parameters. Next one. Yeah. Go on. Yeah. Next. Yeah. Next. You find everything you need for this calculation. You find in this tables. Yeah. Next. Yeah, and coming now to the this is a bit, I want to explain from simple, the example we have skipped and what you can to try to recover. The example was simple. And to give you an idea how complex the situation could be, and was a review from the AAPM from 2014 about the NRCP 151 report. And if you then, and all the mentioned parameters are now much more in detail defined. So next one. You see the workload for the IMRT, for the IMRT, and it's much more different. Now, yes, this is a workload summation. You could see the workload to getting a better. If you want to improve, this is at the end. If you want to improve your calculation, what does it happen? You have to have the treatment. You have to have the radiation protection plan. If you want to buy a new bunker and you want to have a new machine, the radiation protection plan is needed before you start with the construction. That means if you have an error in the radiation protection plan, you will realize this after the machine is in operation. And this is the expensive way to optimize your radiation protection. At the end, you will not get a license to operate the machine until the radiation protection for this situation is correct. So if you have a bad radiation protection plan, this will prolong the installation time for the machine, and it will increase the construction costs. So that's very, very important. I have later on a short diagram how it works. So a lot of more complex examples also regarding the different shielding situation. And you have very nice corresponding calculations are in the safety report 47 from the EIA. It's a very good and very detailed examples. You see here you have examples for orthovolt room and for different bunkers for high and low energy machines. Yeah, next one. And what's coming up more and more, and this was very common. One back, please. Back. Yeah, here we are. It's one step more. Yeah, now we are, and no. Only two steps ahead. What? No.
So this is.
Yeah. No. This image here shows, and this was very common and came up with the radiation protection calculation for the proton units, and these mainly were done with Monte Carlo programs, and this is the most accurate way to do this. And these programs are coming up now more and more, so that you do the calculation of the shielding situation based on Monte Carlo calculations. Yeah, next one. Yeah, and this is what I try to touch. One spec, please.
Yes.
Two back. So now, yeah, this is what you could ask yourself. You will buy a new machine and you need a new bunker construction for this machine. Would you calculate the radiation protection plan for this bunker construction by yourself? You could, but you have completely understand also the complex examples for this calculation and the risk that you fail in one or the other point is high. And at the end, a bunker for a treatment machine is not a closed cube of concrete. This bunker has to be connected to the outside, so to the electricity. You need cabling, plumbing, and all these things has to come into the bunker. So a linear accelerator is a complex machine, and this has to be connected inside the bunker. So you have to open at some point the bunker, and all these things has to be covered by radiation protection calculation. The next one. Yeah, this shielding summary, and this is a very good example from the I've pointed out this of the presentation of Professor Kuchaka. So the careful planning and shielding design helps to optimize the shielding design, and the calculations are complex and must be performed by a qualified radiation expert, and the shielding must be checked by an independent expert to monitor along the term basis. The next one. You see, this is out of how we set it up a machine. You see, we have a tender, to start the procedure. This is on the left-hand side. The bunker construction is based on a given and a predefined radiation protection plan, and we didn't start any construction before this radiation protection plan is proved by an independent expert. Then we have the delivery and the installation based on the vendor's installation guide. And you see here, this is next. Yeah, you could bring it on the next one. Next one. Yeah, you see, this is out of a vendor's installation guide. You have one spec, please. Yeah, you see. One spec, yeah. I know we have a delay. back.
Yeah.
Back. Not for.
This is back. So if I go forward.
Yeah, this now we are right. Now we are at the right position.
Okay.
That's once too much. Next. Now the next one.
Okay. Yeah, this is.
So this is only, and this is from the. No, this too much. This was too much. Sorry.
Yeah. Should we go back? This is one step back, two step back.
One step back. So now this is the right one. No. One more.
This is one more forward. Is it backward or forward? This is
forward. One forward. So now, please stop. Yeah. So this is out of a vendor's installation guide, and you see the room. You need the minimum room dimensions for bringing in and operate the machine, and you see these are the rough estimations. What's about the shielding thicknesses of the bunker. And this gives you, first of all, an idea to compare this with a given radiation protection plan. Yeah, because this is a bit conservative, and this is, I think, this is a rough estimation. The next one. Yeah, what is also pointed out in the vendor's installation guide is a cable conduit, interlock switches, and all these things you have to connect the machine to the outside world to the electricity and everything. You have to operate the machine with interlocks, and these interlocks are connected to the operational area and all these things. So you have to connect this treatment room in one or the other way. Next. Yeah, you do this, and you can have different construction principles. You do this in the, not just too much. One back.
This is one back.
No, let yeah. This is what you have. What you see here. This is a mazeless at the bottom of the image of the slide. You see this is a mazeless bunker, and you see in the front the door is a massive door. The door has nearly the same dimension with like the secondary barrier. So this is a very heavy door. The door has 20 tons, but we had, for this bunker, we had no alternative. We built because the space was limited, and we built the whole bunker out of high density concrete. So we have the investment was, we invest in the high density concrete, and we minimize the dimensions for the shielding. Next. Yeah, this was a consequence. The door has 20 tons. Yeah, next one. Yeah, this is an interesting construction principles we use at one of our satellite. It called the Forster construction method. You have thin concrete walls, and then you have and these walls get filled by a special mineral. So you see, the mineral has not the density of a high density or low or standard density concrete. In that way, the shielding dimensions are higher. But in this case, we are not the owner of the land for this bunker. So if we shut down the machine, we have cleaned the area. So the deconstruction costs are low, because we only have to demount this thin walls. And then you can remove this mineral in the between these two concrete walls very easy. Go to the next slide. There is a bit explain how it works. So you see there are thin concrete walls in the middle, and then you have a mineral. This mineral fill is not massive. It's filled in, and if you break down these walls, these concrete walls afterwards, you could remove this mineral fill very easily. Yeah, next. But you need a higher dimensions. I would show you at the end now how what was the impact. We did an upgrade of one of our machine with IMRT, and I would show what was the impact to the radiation protection. The next one. Yeah, this is a situation. You see the wall 2.6. And you see, this was the dimension with a non-IMRT machine, and you see the point 3B. 3B is a public point, is a point in the public. So we have to achieve at this point 1 millisievert per year. So next one. Yeah, this is a radiation protection. This is a part of the radiation protection plan, and you see the use factor, the occupancy, and all these things. And at the end, you see the required area. The required area was in terms of high density concrete 1 meter and 87 centimeter, and with low density concrete 2 meter and 86 centimeter. The existing way was we had 170 centimeter of high density concrete. So we have the protection was not good enough, and then we have to increase the protection, and we could have an equivalent shielding by an additional layer of 25 centimeter concrete, 70 centimeter high density concrete, 6 centimeter steel, or 3 centimeter lead. At the end, we decide, because the space was limit, and we decide to shield the primary area by 3 centimeter lead. The costs for this were very high and were not really expected at the time. The next one. Yeah, that's the safety report we have to prepare. Next. Yeah. Okay. I think we could finalize this. Yeah. Next. Next. Yeah. Back once back, 2 back. Sorry. No, next one. Once back. Yeah, and you see, too much. Forward, one forward, please. Yeah, you see, no, once forward. Yeah, now it's correct. And you see, when everything is working properly, we had a groundbreaking in May. This was one of our machine. We had a groundbreaking in May 2003, and we were able to treat the first patient at March 2004. But this means from the very beginning, from before we start the construction, we need approved radiation protection plan, and this radiation protection plan covers all the issues where I tried to mention during the last 1.5 hours. Next one. So this is my last slide, and I want to say thank you for listening to me. I hope it was I could explain how complex it could be and what are the solutions to get these things done. If you have any questions so far, please.
Any question? Okay.
Try to work the examples, the given examples in the presentation, or one of the examples in the EAEA report. This gives you an idea how the factors are working together, and what is the way to achieve a needed radiation protected situation. Thank you for listening.
Thank you very much, sir. God bless.
Thank you.
Yep.
Thanks a lot, Volker.
Yep. Yeah.